Hello and welcome to Reactive Programming with Rescaler, a part of the Concepts of Programming Languages lecture given by me, Ragnar Moog. So there are a couple of facets of reactive programming that I want to talk about before we dive into the main part of this video, which will be a live coding session. But there are many things people associate with reactive programming. The first is just a better API for observers, making a well-known concept more usable, more composable, and also giving it more like good defaults and more built-in functionalities. The second is a denotational semantics to reason about values that change over time. This is especially true for function reactive programming if you want to do proofs about your program, but also if you want to have kind of vector graphics, but for videos, where you can zoom in on the time scale in very granularly between each frames, because it's just a continuous reasoning. And the third point is sometimes people associate with reactive programming a preference of responsiveness over everything else, meaning that the most important thing of some applications is that they give you some answer as quickly as possible, even though the quality of the answer may not be the best. But for a wide spectrum of applications, that's the important part. Rescaler kind of is like a design point in between all three of these, trying to have as much as possible from all three, generally preferring correctness over other things, but trying its hardest to be a good point in the design space. And I think it's a point that you should really look at. And even if it's not the right point for you, it has a lot of things that that you should be aware of and maybe should consider when designing your applications. So as I said, the main part of this this lecture will be me live coding a distributed chat application. For this to be effective, you need to be active, right? If you just listen to this video, you get some intuition about Rescaler, but you don't really learn what you should learn in a lecture. So try to work along the video. I try to make the setup really explicit, so that should not be a hurdle. You can also just watch the video and then do it on your own afterwards and maybe consult the video again, but really try to at least play around with the provided code, change some things, see what failed, see what happens. Even if you spend just a short amount of time on that, that will really be super important. And also, the remainder of this recording, well, also this introduction, was done live. So I really do live coding there with basically no retakes. So there are thinking pauses, there is probably some background noise. Please excuse those things. And even more important, I may have not explained some things because I didn't consider. Usually I would do this in a live lecture where people could interrupt me and ask questions. Can't really do that due to the remote situation. But if you have any questions, if any concepts that are unclear, feel free to contact me. It's often just much easier for me to answer a quick question than it is for you to like search what even the question is. Was that said? I hope my video editing will be good enough that we can just jump into the next part of the thing. And I hope you enjoy. Hello and welcome to the live coding session where I try to explain you the basics of reactive programming, given the example of Rescaler, building a small interactive application that runs in your web browser. So as a reminder, this whole thing is meant for you to kind of either follow along or try on your own, but really do some coding yourself, and maybe watch me as like a help in between, or watch the video first and then try on your own, see where you fail. But really this trying on your own part is super important, and I try to really start from the very beginning to make it as easy as possible for you to get started. That said, so Scala has some some boilerplate involved in setting up a project. So this is the first hurdle you will need to take. So you will get from us a template, which I've already opened here, contains some files, most importantly, this SPT build script. Actually, I should probably add one for Windows as well. I think this one currently only works for Mac and Linux. But anyways, so the first thing you should check is that you have a JVM, well, not a JVM, a Java development kit installed. Maybe a JVM is enough. But if you check Java C version minus version, and it tells you a version number that's roughly in the area of above 11, things should be fine. If that's the case, you can just run this local SPT script inside of the folder you checked out, and it should start SPT. It will download a lot of dependencies first, may take a while depending on the internet connection, and then you get this SPT prompt here, right? Where you can compile the code. This will again download some stuff, most notably the Scala compiler, but also the dependencies we use in our program. And right, if this works so far, great. After you've started SPT, what I tend to do is I do my development in IntelliJ. So this is the IntelliJ new project dialog. If you also want to go along with IntelliJ, you may need to go to plugins, marketplace, search for the Scala plugin and install it, because I think it's not installed by default. Not quite sure, but this should be easy enough. And then you may have to restart this application. And then you basically find the folder where you extracted the project to. It should show you somehow that this is a project in somewhere. It also should detect this build SPT, and you can just open the folder. It will ask you if you want to import this as an SPT project or build server plugin project. These are two different ways of the IDE to communicate with basically your Scala project. It doesn't really matter which you choose. SPT currently is the default. I will choose that. If you have not started SPT before starting IntelliJ, you won't get this dialog. You will directly import the SPT project, which may also be fine, but be aware of that. Now IntelliJ will tell you, do you trust this project? Because as you should know, executing any build script will just execute arbitrary code, which could do evil things to your project. Well, I've written most of this code except for SPT and the plugins. I kind of trust it, so we go ahead there. It may complain that your class path is corrupted for some other dependencies you need. This is an IntelliJ thing. And it also now is currently loading all of the basically what IntelliJ does is it runs another instance of SPT, exports all of the project definitions and imports that in SPT. And for this ClassPath plugin, if you have that, I'm not sure, this is the formatting plugin I use. You can just press resolve and IntelliJ will download a lot of stuff. The reason I have to do this is because before I started this whole demonstration, I basically deleted all of the things I had to give you or to figure out what the experience that someone new to Scala development would have, so I can give you some help on that. Once this is finished, you can just minimize this dialog, and then right. So let's first talk a little bit about the project file itself. So this is basically an empty project. In source, you have like a super small template where I mostly included the imports and then created an empty object. There's also this utility thing. I'll talk about this later, but that's basically all the code you have. The reason why we use template is basically for this project definition here. So this is an SPT file. It says, well, we have one project, which I call chat, which is in the current folder, right? So this is just the current folder. So the interesting thing about SPT is it's the build definitions of SPT are also kind of written in Scala or something that's like 99% Scala. So you can do a lot of fancy things, but it tries to look like an easy DSL. So think you should note about this build script. And I know I front-loaded a lot of information here, but feel free to ignore this if it feels too complicated for now. So what we do is we say, well, we want to enable the Scala.js plugin because we want to write a web application. And then we say, well, this project has a couple of settings. First, we pick an explicit Scala version. We use version 2.13. There is a Scala version 3 out there, a Scala version 3 out there, which is a major new Scala version. It looks mostly the same, but some of the syntactic features we use in Rescala have changed and it's not fully compatible yet. So for the purpose of this demonstration, we'll stay with 2.13. Then again, all of the concepts you learn here just apply cleanly to Scala 3 as well. It's not that much different. So this long thing here basically just says that because we do a web application, we kind of want the main method even in our web application. And then, and this is the most important part, we add some dependencies. So first we add two resolvers, which is basically repositories where we look for dependencies. One is JITPAG and the other is our old internal Maven repository. Both of them we need for Rescala and for some dependencies Rescala has. And then we add the actual dependencies, which is, as I said, Rescala. Add a snapshot version because I like things on the bleeding edge. Well, more accurately, I'm the main developer of Rescala. I'm most familiar with the most recent version. I made sure that this one is stable enough for this demonstration. If you see a different version here in the template I sent you, well, I did some last minute updates, but that's that. Then we use two external libraries that have nothing to do with Rescala, which is Scala.js DOM. That is basically a library to manipulate like the HTML DOM, and Scala tags, which is a library to kind of write HTML in Scala. And both of these are very useful in combination with Rescala to quickly prototype like small interactive applications. So that's the build file. And the reason I want you to understand this is because I think this is like a really important part of programming, is actually all of the in-between you need. But let's get some actual things happening here, okay? Well, maybe I should point one more thing out. So this was the chat application, right? Which is this empty template. There's also this this index HTML file, which will basically be the container for application, right? We write a web application, so it's an HTML file that executes some JavaScript. You can look at it, there's basically nothing interesting in here, except for this one line which says, well, we include a script, which is in this folder here, which we have not produced yet. And then because we have this main module initializer thing set in SBT file, the main method of the script will basically run, and then the script does whatever we want with this file. And if you want to test the application, you will have to open this HTML file. So that said, starting with some actual code. So first things first, let me enter presentation mode. So those of you who may have a smaller screen can actually see what I'm doing. So this is a simple Scala file, right? It's similar. So Scala is execution-wise pretty similar to Java. So if you know Java, a lot of concepts just apply. So we do have a package. Everything in Scala lives in a package. If you don't explicitly name a package, we use some default package, which I don't like because it has often like it sometimes gives you these weird error messages where it says like default package or something. I don't like that, so I always go with explicit packages. I have some imports here that will just make our lives a little bit easier because I don't have to search for things and you won't have to search for things as much. I talk about the imports at the points where we use them. And then here we have an object defined in this file. So an object in Scala is well, it's kind of just what it says, right? This is a single object. In Java, these are sometimes called singletons. So whenever you execute, when you run this program, each object definition will just instantiate a single object that is globally available in your whole program, which is very useful, for example, to put your main method in. So we can use some IDE magic, ask IntelliJ to generate us a main method, and it will do so. And we can now, from everywhere in the program, just run chatapp.main to execute our main method, and that's exactly what well, we'll see in a second how this gets run with our small case study. So methods in Java are defined with a def for define. They have a name. They have a list of parameters, and they have a return type, which in this case is just unit, meaning this method returns nothing interesting. The list of arguments, each argument has a name and also a type. So main gets an array of strings, which is the signature of the normal Java main method. So what we want to do here is, remember this should be an interactive application. So we have something interesting thanks to this Scala.js DOM document thing, which is the document, right? The document is the kind of in the HTML web application world, the document is this main thing you see on the page, and each document has a body. And what we will do is we will get the first child of this body and replace it. Actually, what we will do is we will replace a child of the document, and that will be the first child. JavaScript APIs are a bit weird, and we replace it with something. So we'll name this something our contents, and this will be undefined for now. And this here should be our contents. So undefined for now. Let's say our contents should just be a small paragraph of text, right? So we go paragraph. This will be rendered. And we also have to actually render the contents. So now a lot of stuff is going on here. Let me talk a bit about that. So first, a val is how you define new names in Scala. So val content says, well, this is just the name for the thing on the right. We will evaluate the thing on the right, store it in contents. You can also ask IntelliJ to add a type annotation. So this thing here, this P, comes from this nice Scala tags library, where we imported all of the methods. So P is a paragraph. It's just the HTML tag P, and this will generate a paragraph text. I'll show you how this works in a minute. And it returns a type tag of paragraph. So this is mostly useful because we have static type information about the structure of the UI we want to generate, which means we get this nice auto-completion you have already seen. And then at the end, we have to convert this this type tag into, as we have seen here. Oh, actually, this is the wrong order. Haha. So we should have the new child first and the old child second. So see how important auto-completion is. So we can see here this one's a node, not a type tag, and render is how we convert a type tag into an actual node that we can put into the DOM. Right. So pressing Control B in my case, we can try to compile this, which has to start SBT, and then thus takes a while, but should get much faster after it. So no problems, a lot of warnings, which are these unused import statements. No issues here. So let's get back to my console, right? I opened the project in SBT at some point, and I like to also compile in SBT, mostly because IntelliJ sometimes doesn't really show you all of the error messages or shows you different ones. It usually works quite well, but who knows. However, what we actually want to do is, now we have a program. We can run it, downloading some stuff because I didn't do that before. But as you can see, nothing interesting will happen, or more correctly, this will crash because we ran kind of something that we expected to execute in a web browser, but we run it in a console that doesn't quite work. So what we instead do is we produce JavaScript code out of our program. And that happens with a command that's called fast.js. This is an SPT command that will just compile our program into JavaScript. And has been pretty quick, actually. I did not expect that. Refreshing our project, what we can see now is we have this target Scala to 13, and we now have a chat fast.js. So this is actually the compiled code we have. And if we go back to IntelliJ and open our project view, I had shown you this index.html, right, which opens this fast.js, and it's the file that was just generated. So I think we can open this here in a local browser, let's say Firefox, and then jump to Firefox, right? And as you can see, you can close these. There's this will be render text, which is exactly what we wanted to output. And if we inspect this using our right. So this was a bit of an the way this works complaint, but ignore it for now. We ignore it? Can we ignore it? Is it fine? Right. Let's see. Right. So as you can see, what happened is that, so this is the document that we have in our code, right? And the document has a body. And what we did is we replaced the first child in the body with this will be rendered thing. So what is the first child? Should have been this section here, but seemingly the section remained. Well, I won't pretend that I fully understand all of the HTML working, but as we can see, this piece of thing that we wanted to render has been output here. Amazing. And is the first child that is replaced? So there's another thing we could do is well, let's leave it like that for now. So what I like to do is I like to put my program into like reasonable like logical chunks. So what I will do is I will take this thing here on the right and replace it with a function call. We will define a new function that call get contents here, and IntelliJ nicely auto-suggested the name because it wasn't defined yet. It also shows us what the current type is. So this allows us a little bit to talk about the contents separately from the from this main structure of the application. So for this get contents method, what I would like to do first is I would like to make the application actually a bit interactive. And for that, we use an input element. So input is, well, you'll see. This has a placeholder, I believe. Yes. The placeholder will be enter some text here. And English spelling doesn't do capitalization. So this, knowing how this works, still all plain old HTML. Placeholder is just another HTML attribute. Nothing fancy going on here yet. However, now I want to add some interactivity, right? So what I would like to do is I want like this text to be displayed in this P here. And for that, we will use rescaler for the first time. So the way rescaler works is that it provides you these abstractions for reactive programming, but you can integrate it with a lot of different like external worlds. One of the external world being, in this case, this whole HTML space, right? Which is why we had to do all of the HTML setup first. But now, so I cheat a bit. We have this render util, which has this one method called input field handler, and so let's store our input in a val, and we can now pass it to this render util thingy, and tell it, well, we would like to handle the on change, I believe. Is it on change? Let's look. Right. So there's on change and there's on input. I want the on input in this case. Where the difference is, on change is basically whatever the browser considers as a commit of the text box, which usually means hitting enter or sometimes defocusing the text box. Whereas on input means every time we enter something. And I would like the text box to not be cleared when this happens. Right. This render util will give us a result, and it's always interesting to inspect the type of a result. So now this needs a bit more space. So the type in this case that the input field handler method gives us is a rescaler event. Let's not use the default here. This was a bit IntelliJ being confused. And let me also format the code nicely again. So the result contains a pair. So this parenthesis means this type is a pair of an event of strings and a rendered input. So the rendered input is again our text input, and this event now is interesting because this is a rescaler abstraction. This is something we call a reactive, and this event will be triggered every time that that this input field handler changes. So let me try something a little bit unexpected. Clone. Great. Actually, let me go one step further. If you have a tuple like this, right, you can go result _1 and _2, which accesses the two elements of this tuple. I kind of really don't like to do that. And instead, we will use a Scala feature to destructure this tuple. So when you define a val, you don't have to just put a name. You can also put a structure in there. So in this case, that would be the text event and the rendered input, and then assign this to result. So basically what we say here is result is a tuple, and we destructure the result into these two components it has. So we can access them by a nicer name than _1. And now we want to go ahead and say, well, text event observe. So observe is something that that's offered by rescaler. It has this horrible type signature that you should just ignore. The important thing is it has the string to unit method. So observe takes a function as the first parameter, and for such things as Scala, we typically, so you can call a function with parentheses, but you can also call them with braces. And usually, if you pass a function to a method, you put them in braces. function here, meaning that we say, well, we have really a text, and we do something in case that text happens. So this is a function body. What we want to do is, I believe this is window dot alert. Yes, very, very classical JavaScript thing. We have a text box, we want to enter something, and when we do so, we put out some alert. Right. And now nothing will yet have happened because we still return this paragraph. So instead of returning the paragraph, let's return a div which contains our rendered input. Right, so we will have the input field in there. And just for testing, let's change this to on change again and say this is clear through. Reasoning here being that if we have, well, you see, we will see. So we go back to SBT, which is not here. I should move it here. Nope. Sorry for the confusion. So back to the SBT console, back to fast.js. And if you always do this, there's an interesting trick. You can do tilde fast.js, which will cause SBT to look for changes, and whenever a change happens, will automatically call this, so you can, so you don't have to type it again and again. So back to Firefox, reload the page. We have this nice text box. We enter the classic string that everyone knows and loves. We hit enter and we get our alert box. Amazing. So now you know Rescaler is just a glorified way to write very complex observers. Well, it's not, but it can be used as that if you are so inclined. So this is the observe code. So what's going on here, right? Let's talk a bit about the execution order. So we create the text input. We add somehow a handler to this input. We do this destructuring to get the rescaler event, and then we have the observer that executes just some code again. So basically, we have some external thing, external from the point of view of Rescaler, which is the HTML world. We convert to Rescaler and then immediately convert back to the imperative world HTML, which kind of didn't make use of anything interesting in Rescaler yet. The main point, or one of the main strengths of reactive programming, is that these events here, or reactives in general, event are like a special case of a reactive, are composable. What does that mean? Well, let's say we again, let's go back to our on input here and clear false. And just to show you why I didn't want to do that in the first place is if you replace here now, if we just enter a single letter, then we will get the we will immediately get the alert, which is a bit annoying because we can't put in more than one letter. However, this is exactly what we want if we want to, for example, show the content of this input somewhere. For that, let's remove the observer. We don't need that. Instead, what we want to do is we would like to have, inside our output, we would like to have a paragraph, and this should be whatever is the content of this text box, right? So what maybe you think we should do now is take the text event, and whenever the actually, excuse me, we do need the rendered input. Yeah, we still need to keep that. So what you might think is that, and we in addition to this rendered input, we want a P that has changing content. And what you might think is that, okay, somehow we observe the text event to change this P. Well, that's not really what we want to do. Instead, what we're going to do is we're going to define a signal being a value that changes over time, and just put the signal inside of our HTML. So text event, right? Text event again. Maybe let me, one simplification before. We currently have this val result, and then we immediately destructure the result. We don't have to do this duplication. We can just have the destructuring here, right? Just syntactically a bit shorter. So we have the text event here, and the text event is an event of strings. Events being like things that occur occasionally, but we want to have a value we can always display. And to do that, we say, well, we want the latest value here. So the latest event, we want to keep that and hold on to it. And we say, well, we initialize it with nothing yet, just as a placeholder value until the user actually inserts itself. And we call this here the text signal, right? And we can ask IntelliJ again, what the heck is the type of the thing? It will add the default because it doesn't understand that it's already imported for bad reasons. But this is a signal of strings. Signals are a lot like events, but as I said, where an event only has a value at the moment that that the thing happens, at the moment where you hit enter, at the moment where you press the button, the signal will always have the value and just keep being updated every time this event changes things to its latest combinator. So what we can now do is we can take the text signal and map it. So I'm not sure if you're super familiar with these functional combinator concepts, but mapping usually means I have something that contains a value and I would like to apply a function to this inner value. And that's usually what you use a mapping for, where the name map really comes from this, right? This physical map, right? Like a map of a city where each position on this paper you have is associated with the physical position in the real world. So there's a mapping from one position to like a different position in a different space. That's where the name comes from. So again, name takes a function, so we use braces here, and we take our string, right, which is the thing inside of the signal, and we would like to have a p that contains this string, right, where p is again our paragraph. So this is now a paragraph signal. It stays a signal. Map does not remove the outer thing, but it changes the type of the signal to be a type tag of paragraphs. And lo and behold, we can now put this signal inside of this div, except that we can't quite put it in there. We have to say, well, we would like this to be a modifier. So modifier is a name that comes from this library we are using. So div, as I said, is from the Scala tags library. And as modifier is just a conversion that converts this signal of type tag of paragraphs into something that this library understands. That's something that comes from this import up here with a Rescaler extra tags. It's like a compatibility layer between Rescaler and this HTML library. So we save again. As you might have remembered, SBT in the background is compiling. Seems like it has been compiling just fine. So we can look at Firefox, update the page again, and can see, well, we have entered nothing yet. So let's enter something. Lo and behold, the paragraph updates as we put text in this input. Right. So if we go back to the code, you can see that there's nothing really left that looks imperative here, right? We just define a text input, we define some input handlers, we derive some signals, we put something in the DOM, and we put the DOM up here. Well, this is actually a bit of imperative code where we place a bit of a DOM, but that's not part of Rescaler. We put it on the page, and once it's put on the page, everything just updates automatically. And this is a very fundamental and core concept of the power of, well, not even reactive programming in particular, but really of declarative programming. We just say what our program should behave like. And let me just auto-format this again to get the spacing nicer again. Right? So this might also not yet be very impressive to you, because, well, you know, you could probably have done this using some imperative event handlers, whatever. However, we can now make things a little bit more, well, more complicated, more interesting. Let me remove these things, we don't need them. IntelliJ likes to add imports we don't need. So I said we wanted to go do a little chatting application, right? So we now have an input where we can put some text, and I will repurpose that for entering your name, right? So we want to allow the user to input a name. In addition to the name, let's rename this here to name input, and this here will be the rendered name, and this here will be the name event, and this here will be the name signal. So I think renaming things is very important, because if you give things a good name, it's much easier to understand your program. I'm not saying that my names are good, but try to have okay names. Now we will use the most important programming trick ever, copy paste, and add a second input, which will no longer be the name input, but rather the message input. This will also be an input, it won't have a placeholder, won't need one. And this one will have a, will again have the message event and the rendered, well, the render message. Same things here, but this will be an on-change handler, and we will clear it when we enter it, right? The idea being we put in a message, we hit enter, the input text empties, and the message is sent to the chat. Name signal stays as it is, paragraph signal goes away. Now, let's think a little bit about what we have to do. So one thing is, we not only have the rendered name, but we also have the rendered message, right? We want to display both inputs. So we put them just next to each other in this div. Nope. This one here is gone. But we still have to somehow combine these things into a message. So what I like to do is, okay, maybe a different thing. So what we want to do is every time the user presses enter on the text input, we want to somehow read the current name and combine these two things into something we can display. So a pretty straightforward thing to do that is like, so we call this a chat line. So we want to do something, or we want to create a new value whenever we enter a message. So we take the message event and we again map this thing. And the message event contains a string. Well, maybe let's name it message because it's a bit more meaningful, even though we have many messages already. I like giving things and functions short-ish names so they don't clash with the outside things, where the outside things get longer-ish names. So what we want to do is we want to combine the message and the name. So inside this map here, what we can do is we can ask the name signal for its value. So this value thing is something you can only do inside of what we call reactive expressions. Map being one of those. So you can only access the value. You can't. Okay, let me make this clearer. You cannot really read the value of a signal outside of the code. If you look at the implementation, you will see it will just throw an exception. Actually, it won't even compile because it's a compile time only function. There's a bit of syntactic magic going on here, making that possible. IntelliJ doesn't understand it. It doesn't show it in red. But keep that in mind that whenever you see like signal or event.value, that's something inside of an expression. And what it means is that when the message event triggers, we will take the message and we read the current name. Now we want to combine that with the message. And Scala has this nifty string combinator expression. So let me copy paste this one here for a moment. Well, cut and paste this one for a moment. So if you say S and then start a string, you can basically build a string with a nice syntax. So you say dollar and open close parenthesis and put in there some code. After the closing parenthesis, you are in a string again. So we say just colon, and then we open a dollar again, put the things and say, well, we want to put a message there. So we build kind of just a string out of the value, a colon, and the message. And that will be our chat line. Now, question for you. What's the type of the chat line? Well, ask IntelliJ, it's an event of string again. But let me leave out the this thing for now. Now, we'd like to have every line of chat displayed in our div, right? But currently, we only have single lines. We somehow want to collect all of the lines into a thing. So what we do here is we name this history. And if you think about it, the history, right? What should the type be? Well, it's clearly a collection of messages. But every time a new message arrives, this collection of messages changes. So it's a time-changing value. So it is a signal. And a collection in Scala is well, the simplest collection is a list, and it's a list of strings. So how do we get? Let me keep the type annotation here. So how do we get a signal of list of strings from an event? Well, gladly, this is a pretty common operation. So there is actually a built-in function for that, which says, well, would like to have just the list. And this is the internal implementation, which I sometimes look at to see if it actually did use the right function. Now, this is a list of strings. We can't quite display a list of strings inside of an HTML tree because HTML can't really display, well, Scala strings. What we want to do is we want to actually put each message in its own paragraph so that the spacing is a bit nicer. So we define a chat display and just say, well, we take the history and we map it, right? We can map signals, and we take here the chat lines. This is a list of things, right? It's a list of strings. And the way if you want to modify this whole list, right? You want each line to be a paragraph. You say, well, we take the chat lines, and we again map this list. It's the same thing. Well, it's similar to mapping events and signals, right? We want to keep the outer thing. We want to keep the outer list, but somehow change the values. So again, using a map here, where we have each individual line, and we just say, well, we wrap the line in a paragraph. which will give us a signal of, set the type annotation to make this easily visible, the signal of lists of type tags of paragraphs. Which is amazing because, well, not amazing, but you know. So let's put this in another div just so the things are a bit nicer, and we can just put the chat display inside here. And again, this is we have to convert this to a modifier, but not to a normal modifier, but to a list modifier. There's weird technical reasons why there's a difference between converting a signal of a type tag versus converting a signal of a list of type tags. Basically, it's a performance optimization, but the L here stands for list. Now let's see if this compiled. SPT seems to say it was fine. So looking at Firefox, updating here, I enter my name, which is Ragnar. Okay, I have another username, which is interesting. Say, hello, world. And this seems to have worked. Seems to work. Amazing. So we add new messages seemingly at the top of this thing, which may be what we want, maybe not. I think not. So let me first figure out why does the second input have a placeholder? Unclear. Aha. See, there's a message input, but it here says name input. So I use the name input definition up here, which is the input with the placeholder instead of the message input, which is the input down here, right? But otherwise, the two definitions are the same, so it doesn't really matter which one I use. And these are still two different inputs because I put them twice in the DOM, and that caused actually the rendering that happens inside of this input field messages, what kind of causes them to be two separate instances. But anyways, so this should fix the this placeholder thing. The other thing I wanted to fix is we didn't like that that this history here is in the wrong order. So well, we have a couple of possibilities. What we could do, we could, for example, just say here we want to reverse this list. So if we compile that, actually it doesn't matter. What matters is that FBT does it. If we reload here, hello again, and at a second line we get it below. And I hope you see a little bit that that this allows you to have actually quite like you actually have quite a bit of flexibility with signals and events, because you can combine them arbitrarily. You can do a lot of small modifications that are very declarative, right? Each step is very easy to understand by its own, and then the runtime takes care that updates happen realistically. Well, not realistically, but in a way that makes sense, in a way that doesn't break your application. There's actually some more interesting things that don't quite fit this pure chat example anymore, but that are kind of neat to show off, which I want to do now. So, but first let's clean up the code a little bit. So what I don't like is this weird creating a chat line string here, because we lose information, right? We combine these two things into a string, which we don't yet want. So let's define a new data type that describes a chat line. So this will be a case class. So classes, I hope you know from many programming languages, right? It's like of a definition for a data type. Case in the case in Scala just means that this is a data class. So we call it chat line, and we give it 2 parameters. So classes in Scala can have parameters. We give it an author, which is just a string, and we give it a message, which is also a string. So you could, for your understanding, write the val here. So these are values. In the same way that values inside of functions are values, or in the same way that you could write a val in a class. But because it's a case class, all parameters are values automatically, so you don't have to write it. So, and when we don't have to write, we usually just don't write. And this is all you need. This is a full definition for like a small data type class, like a struct in C, like value classes in C sharp. Like actually, I think record types in Java. Java has it by now as well. It's a simple concept, but sometimes people have not seen it yet, so that's why I talk so much about it. And what I want to do is I want to take this thing and say that, well, chatline is now an event of chat lines, right? And instead of generating this string down here, we will just say, well, we want to create a chat line with the name signal, but the value of the name signal and the message. And our history can be a history of chat lines, right? And other, well, a list of chat line. And then we can do this mapping here below. So there's one more, because this whole thing here got a little bit complicated. I want to show you one more nice syntactic feature of Rescala, which is signal expressions. So we remove all of this. We're going to rewrite it, and we just say, well, this is a signal, right? That's what chat display was before. It's a signal, and the signal is defined by just taking the value of history. Again, this value method is the same value method that we used up here, and signals is a signal expression similar to how map is also one of the reactive expressions. The only difference is that the signal expression will kind of listen to changes to whatever is inside of here. So history.value will give us the list. Now we just have a list. We want to reverse it, right? That's what we did before. We could just say reverse, right? Just give it a name. Maybe reverse history. I like naming things that makes the code more understandable. And again, map the reversed history. Mapping again, just a normal thing on lists. And we want to say, well, we get this chat line here, right? And what we did say is, this is a paragraph cat line. Well, it could also be a cat line as a paragraph. And again, we do this string concatenation where we say, well, we have chat line dot author followed by chat line dot a message. So nothing has really changed. It's just a little bit more well, a little bit more systematic. Also, I can show you another couple of nice features in a second. But first, let's test that this still works as expected. So I'm still called the same. Again, second message, and still everything goes. Actually, maybe I should also point out that we can change our name. Right, we'll get new names here. Right, so back to the code. So one more kind of neat trick. Currently we do this chatline and I do chatline.author and chatline.message, which is a little bit verbose. And similar to this destructuring we had up here, right, where we destructured a tuple, we can destructure these case classes. For that, we have to say case here. We need a keyword because Scala. And then we just say, well, we say chatline and IntelliJ autocomplete this, which has an author and a message. And then we can just use author and message here. It's a little bit shorter. And also, if it's a single name here, we don't need the parenthesis, and IntelliJ actually has a what is automatic refactoring for that. So this is a little bit nicer, but doesn't change much yet. However, what I wanted to show you is that you've seen that we can change our name, which behaves as expected, but we can do something more interesting and keep our name variable even for past messages. So say we have this chat line, and instead of a string author, which is a fixed value in time, we say, well, maybe the author is something that changes over time. So we can totally just put a signal inside of some other class as a value there, right? Signals are also kind of just values. And then IntelliJ will tell us what went wrong, because now the chat line is a name signal value, which is no longer, it's just the name signal, right? We just pass the signal when we create a chat line. This here stays the same, but now this author here is no longer a string, but is an actual signal. So we have to add the things again. We now access the value of the author only when we create the message. So you may think, well, there's nothing different here yet, but it actually is. So one interesting point is if you try to compile this, let me see if IntelliJ says this nicely, right? So Rescaler will complain here that the access to this reactive, the author signal, may be dynamic. Where it means, well, this author signal came out of this chat line came out of the reversed history, and this reversed history came out of some signal I've read. So Rescaler doesn't really know statically what this thing is, which in this case is fine, but you have to explicitly say, well, I want a dynamic signal expression, because actually, like, these dynamic cases are a little bit rare, and it's better to explicitly ask people to, hey, did something go wrong? Is that really what you wanted? And if it is, just add the dynamic and then you're fine. So now we have this dependency on author value when we display this time-changing history of messages. So what it means in practice is not much yet, right? We still have a message and a second message, but if I change my name to something else, then it will change everywhere in the list of things. I can add a third message, and so on, and change my name back. I mean, for chat, that doesn't make much sense, so we will undo this change, go back to authors just being strings, and reading the name of the author in the chat line event, right? And this is really what makes the difference. When we read the signal as part of the event, we will get a snapshot of the value of the event at that point in time, whereas when we read the value of the signal, when we display the time change value inside of another signal, then this whole thing will change based on this signal, right? Because there's the semantic of events being points in time and signals being continuous changes. As I said, this dynamic changing example is not super useful for the chat, but maybe super useful for other kinds of applications. It was a small cut in the video for me to prepare for the next steps. But before we get to them, let's talk a little bit about the semantics of this program we have constructed here. So I've drawn the data flow graph, which you can see here on the right, where basically the external world I draw is this diamond. So whenever something in the external world happens and there's a change, we have this name event and message event, right, which we constructed here in the beginning. From the name event, we derive just this name signal. And then from both the name signal and the message event, we derive this chat line, right? There's this this correlation, and then from the chat line we derive the history, from which we derive the display, which again we present somehow in the external word. And one of the defining features of rescaler is that when you, for example, trigger this message event, it will compute all of the reactives that are derived from this message event and change them in a single transaction, meaning that it's guaranteed that for each external input from the external world, there will also be only one change to the output to the external world. So there can never be a weird interleaving of events that arrived at a different time. And also, if the graph, the data flow graph, splits the data flow and there's multiple paths that come together again, then things will be combined as you expected. To show you what that means, I want to add a new little path from this chat line here down to that display, where essentially when we have a message event, it could travel down this line here from the chat line to the display, or the longer path over the history. And the point I want to make is that no matter what, the display, whatever is shown at the end, will only be computed once in a consistent state that kind of makes sense, assuming that each input causes one single transaction. So for that, we have to again be a little bit contrived in our example, because to make the example not too complicated, what I want to do is I want to add a new style to chat messages, and I want to have the last chat message to be red text, so that we can more easily see that. So the way we define styles is we just take this paragraph element, we add a style header, and we set the style to color red. By the way, I think I didn't explain that properly, but this colon equal thing is kind of part of the DSL we use to build these HTML blocks that combines these attributes with their values. It's not actually anything that has anything to do with Scala or Rescala or some such. It's just part of this this HTML library. It's also not a built-in thing. It's just an operator like many other operators. Whereas, for example, this right arrow is really a built-in Scala keyword. It's a different kind of thing. Anyways, so if we now look at this, compilation finished. Let me find our browser again, reload, add my name. Now all our text is red. So we only want the last line to be red. So how do we do that? Well, we could obviously just take the easy case, right? Find out somehow, well, not the easy case, but we could just, because we know kind of what the last message is, could only style that. But as I said, we want to be a bit contrived here. So we kind of find the last added line by just saying, well, the last added line is whatever currently is in this chat line event. This is something we have not done before, right? This is a signal expression, and now we read the value of an event. As I told you before, events don't always have values. We can still read it, but the result will be an option of chat line. Option is a very simple data type that is either none or it is some chat line. So it's kind of like you would expect a null to be in another language, but expressed as part in a type system. So if the event currently doesn't fire, then this will just be none. And if it has a chat line, then it will be a chat line. And now we kind of want the style string, right? So this should be this one, to be dynamic depending on whether or not the current chat line is equal to this last added line. So we say here, well, the style string, if last added line, this is an option, So we can't directly compare it. Actually, we can. We can just say it's some, right? It's not none, it's some chat line containing author and message. So what we do here is whatever we deconstructed up here, we just reconstruct down here. Equality on case classes doesn't depend on like object identities or something. It really just depends on the contents. So if the contents of the last edit line are equal to the line we're currently trying to display from our history, then the style string should be color red. And else, the style string is just empty, meaning we have no particular style. Now IntelliJ already kind of complains here that this code is a bit inefficient. What we can do instead, for an option to say, well, it's equal to some chat line, we can just say, well, the option contains that chat line, which really does the same thing, but a bit more efficient. Now, let's see, did we compile it successfully? Yes. So back to our text, reload. Hi, another line, and the last line is highlighted. Note here that even if computation were to take a while, if there was any kind of hang up in your computer, if it's very slow, there would never be the case that the previous line is still highlighted or that the last line is somehow not highlighted, because there isn't two changes that add the line and make it red. It's really when it's added, it's red, and the other one's not, right? Because as we've seen, there's this combination, and when history changes, chatline always changes, or the other way around, and display with it. Like these can never, there's never like a case where only this pass or only the other pass is triggered. And display will always kind of wait until history is also computed before reacting to this path. It's really like, we shouldn't think about this kind of data flow graph as something where events slowly trickle through, but really something where everything is kind of computed at once. That's the semantics of a rescaler. Now, this was a little bit of a sidetrack to make the semantics a bit more clear. What I want to do now is, well, this is a chat, so there's a couple of features that are a little bit missing. One is a bit of the inconvenience that if we reload, we lose our history, we have to re-enter the name, that's annoying. And also, well, we can't chat yet, right? There's no distribution. So let's go ahead and add that. And the point here is really to show that if you use a programming model like Rescala, a lot of these extra features suddenly become super simple. So first things first, I'd like to keep my name when I reload the page, not history, just the name. And I'll cheat a little bit here. I added I'll added a little helper method, which has this storing method, which uses, well, not a storing method, it doesn't storing object. Actually, let's look at it. So I added a little bit of code. This will also be in the template. I didn't explain this in the beginning. Where we have a new object, right? Objects you can just globally always use if they are in scope. And it has the stored as method, which basically does some of these imperative interactions. So it's kind of an internal rescaler method, kind of. But it uses this DOM window local storage to store information in your browser storage. How does this work? Well, we have to give things a name. This is the key under which they are stored, and we just name the name. Ha. And then we need a default value. So I'll use an empty default here, even though we had a different default there. It's just a bit nicer in this case. And in addition to the default, we now need a, well, not in addition, but based on this default, we now create the signal inside of the stored as. Right. Now what IntelliJ complains about here is that that we need a codec to encode the string into something that can be stored in a local storage. And I also prepared something for that. So let me make that fully encoded. So we have a codecs class. I can also show you that. So this codecs class basically just has a string codec. It's an implicit val. This is an advanced Scala feature. Don't worry about it too much. It basically just says that things that look for implicit values may be able to find this if it's in scope. And the string codec is just, I use another library for that, which is called JSONwriter. And would say, well, make this codec, and it does it automatically based on some implementation magic. Not too important. You can see I have some more codecs we'll use for distribution just in a bit. So going back, we import this codec, and now the stored as, which maybe to show you the other part, here says I want a JSON value codec for A, and this is looking for implicit parameters. So that's how it works. Now finds this implicit parameter, kind of knowing how to encode strings. So there's one more a little bit not so nice part, is that this will be enough to actually restore the current name, but there's also this name field here, the rendered name. And we also need to restore that because really this input is part of the external world. It's not managed by Rescala, sadly. So we also have to set that to the init value manually. And this is a bit of an imperative code. This is unfortunate from my point of view, but this is again because it's part of the integration with Rescala, not part of Rescala itself. So let me see, did we compile? Yes, so let's reload. Ragnar says, hi. As you noticed, hello world became too long for me to type. Let's add another message for good measure, reload, and lo and behold, I'm still me. Great. So let's do the same thing for the message history, right? So that also the message history is stored. So we have a little bit of a problem here. Well, it's not really a problem, but a little bit of an inconvenience is that list doesn't actually take a default parameter. Right, it just starts with the empty list always. So what we do is we could look at the implementation of list, or, well, actually let's not. But really list is just a convenience combinator for a more powerful generic construct called fold. So folding you should maybe already know from other collections. What folding does, it takes an initial value. So in this case, this was a list of empty. Well, it was an empty list of strings, which in Scala you write list of empty and you give it a type argument so it knows what the type of list, well actually it's not a string, it's a list of empty chat lines. So what folding does, it starts with this initial state, and then takes a function that takes the current state and well, a line, right? The second thing is whatever in this event, whenever this event triggers, will be the second thing. And the current thing is initially the empty list and then is updated by the fold. So one maybe small confusion. I told you about this destructuring. This may look to you like destructuring is actually not. This is just a function that takes two arguments. It looks very similar to destructuring, to this destructuring of tuples here. That's by design. That looks similar because it is similar, but it's technically not quite the same. So you don't need the case keyword. Anyways, what we do is we take the line, right, and we prepend it in front of current. So this colon thing is basically the way how you add a single element in front of a list in Scala. If you know about singly linked lists, this is kind of the the core thing in many functional programming languages. If you don't know about it, well, this is just the way you do it. You could, I think, also say current dot prepend, which if you really like your methods, then you can do that. As you see, prepend is just defined to be the same thing. So that's the syntax we're going with. So this will actually do the same thing. To prove that, let me reload this. Add one more line. Right? Nothing changed. But now we have this initial thing here. So again, we go like, we take our storing helper method and say this is stored as the history. The initial value we had already defined here. And let me get the parent. What did I do? I wanted to delete this one, not everything. Right. And we start here with an initial value, and we fold based on this initial value. And again, right, we actually do need a codec, which I did not prepare. So let's quickly go ahead and add that. We want a new implicit val, which is a list codec, which will just be JSON codec maker make list of jetline, right? So again, the library in this case just magically creates these JSON value codecs. Actually, the implementation is a bit interesting, but I'm not going into that. But if we have a JSON value codec, I can also show you this. A JSON value codec basically has a decode value, it has an encode value, and it has a default value. So the library knows how to write things to these JSON readers and writers. So we store these things just as JSON in the local storage. Nothing too fancy going on here. So again, our history is stored as a history. It starts with this list of empty chat lines, and we fold the same as we did before. Let's see if it's compiled. Yes. So let's reload. Hi. Last time this is empty. Yay. I'm out of creative ideas, I'm sorry. But if we now reload, the history is remained. And if we look here on the right, where you can already see I already show the local storage, which just has a name, and it just has a history, which is just the JSON encoded kind of history list. And nothing too fancy going on here, but just some niceties. And the reason why it's really so easy to just add these stored as things is because no matter where the change comes from, right? If it's a chat line that's updating, or if it's the program that's loading and starting with some initial value, we just declare in rescaler how values are connected to each other. So it doesn't matter where the changes come from. The programming just the UI is just kept up to date. Right, that is that. Now the actually interesting part is the distribution. So there are some more complications involved in distribution that I won't go into. I have a little bit of more stuff prepared, but you'll see how it works from a developer thing. So first we need some more UI for distribution, namely to connect to other instances. So we're going to append things. First, I want to append a little spacer. So we add a P that just has a height of 3 elements. And we render that because only rendered things can be appended. And we're also going to append a different thing, which is we have this WebRTC handling. This is also part of the template, which is a class that needs a registry. The registry is, well, new registry, I think so. So this is another library we use, which is called Scala Loki. That's also developed in our group, which allows for basically devices to communicate using relatively simple abstractions. And the registry is kind of a place where you can put values that can then be accessed by other peers in a network. And this WebRTC handling has a single function, which is the WebRTC handling area, which returns a tag, which we just render. Yes. And if this has compiled now, I can show you what it means. So we have a little bit of space, and then we have this area here where we can host and we can connect. However, this will not yet do anything because we haven't connected it to our application yet, right? We just connect things, and then the registry can store values and can communicate, but it's not part of the program yet. So let's fix that step. So what we need to connect is this history. Because the way Rescaler works is we don't really want to connect individual chat lines. The reason I'll show you in a minute. What we really want to do is we want to say, well, the history of chat messages between two peers should always be the same. And to do that, we need a special kind of data type that allows the history of two devices to be merged into a single history when they communicate. In our case, this data type will be an RGA. Let me see if we can find the correct import. Right, so it's rescaler, extras, lattices, sequences, RGA, RGA. I know it's a mouthful, but that's where it is. And we also, I think, need the just RGA without the type. Don't be too confused. This is not yet greatly named. All of the stuff I'm going to show from now on is a little bit experimental, which means it works well, but some of the APIs are still in flux. This is now an RGA of chatline. An RGA is basically a replicated growable array, which just means it's a distributed list. It's a list that you can have on multiple things. It doesn't start with list empty, but it starts with RGA empty. And we don't do line prepend, but rather we really just do current dot. Do we have a prepend? We do have a prepend. So let's just do prepend here. So now this is a signal of RGA, which is more or less a list. You can't quite use it like that. So we don't have a reverse, we don't really have map, but we do have two lists. So we distribute a data structure that's suited to distribution and then just convert it to a list and use it as it was before. So with this done, let me just show you that the application still works. So it didn't reload, reason for that being that we changed the data type, so it can't really reload this. It's not a list anymore, right? So it couldn't reload the state, so it just clears it. It's kind of like a little bit of a inconvenience, but hi. Another message. So reloading again still works. RGA doesn't work any different than it did before. We're still not distributed. There's one thing missing. One small step, and that's we have this this network, which again is part of this interaction with the imperative world that Rescaler has. And the network, we just tell, well, here's a history. Well, not a history. Here is the thing we want to replicate, which is a signal of such a data type. It does need a registry. That's kind of the thing where we want to replicate it, and whoops, and it needs a binding. The binding is a Scala Loki feature that's quite nifty, which basically you give it a name and it computes for you how histories are serialized and stuff like that. So let me see if this compiles, because IntelliJ complains. So basically, Scala Loki tells us, well, somehow I don't know how to serialize this RGA. Maybe you should add this import, which basically says, I've already imported the codecs, but Scala Loki does not yet know how to use that codec, so import the part that tells me how to use it. Let's do that. La la la. Compiling. It's a good excuse if you don't want to work. So let's see. SPT has compiled. Let's reload this. Nice. Nothing interesting had happened, but let's add another browser to the mix. So here is Chrome and Firefox. So let me rename myself to Firefox and this instance here to Chrome. And now we can press the host button, which gives us a string, which you can add on the Chrome side and click connect. Then we can copy the string on the Chrome side to the Firefox side and click connect again. So the reason for this two-way handshake is because of the way WebRTC works. It's designed usually that you have like a central server that does this three-way handshake for you, and after that the two instances are directly connected. But for our case study, I didn't want to add a central server, so kind of you have to manually get the string across, and the easiest way for case studies is just to copy it in clipboard. But you could send it, via another messenger to a friend and actually do remote communication. And now we can add messages on one instances, messages from the other instance. It just works. And the reason why we don't just send simple messages is, say I reload one of the applications, which causes this connection we had to be lost because reloading Windows, it doesn't reconnect. So, oh no, we are disconnected. What should we do? Help. So both of these devices can keep kind of chatting, but they are not connected. However, once we re-establish this connection here, what you will quickly see is that suddenly they are connected. And none of the messages are lost. And even more interesting, all of the messages are in the same order on both devices. So this data type, the replicable growable array, kind of, and the replication logic of Rescala kind of fixed the additions to the list after the fact on the connection, causing both sides to be the same. And then because Rescala just always makes sure that everything is consistently updated, UI updates automatically. So to recap a little bit, what you've seen is that basically the difference, okay, before we had this chatline.list, but the chatline here, the only thing we needed to change was use an RGA instead of a list, right? And then we use prepend instead of the list : because the : is really just for lists. And that's the only really real change needed, right? You use a replicatable data structure, you use the operations of the replicatable data structures, and then you nicely ask the runtime to just replicate this thing for you. And as soon as the registry is connected, that's what this connection dialog does, right? It connects two registries on two different devices so that they can communicate. Everything's updated. And you didn't have to change anything. Well, you had to add this to list. But for the distribution to work, for the updates to be transferred from your inputs or to your outputs, nothing needed to change. Only this piece in the middle had another. Maybe let me go back to Excalibur. Basically, what we did is we now add this this new network thing here, which kind of connects to the history. And when we have a second device somewhere, right, we just have we have these double-edged. Can we make them double-edged? Let's see. We can. So basically, we now have. Oh no, one got lost. We kind of now have two devices, right? The Firefox instance and the Chrome instance. And this history reactive is kind of connected via some another external factor to each other. And this external factor in this case is also managed by Rescaler, such that everything works nicely. But all of the other updates, the rest of the program is completely unaffected by this additional interaction. And this is one of the real strengths of declarative programming models like Rescaler, is that you have this modularity where you just have these composable pieces of your program. And if you add some new complicated additions, new ways that values at some point are computed, it doesn't affect the rest. And because we have like strong guarantees, I know that's not super visible in a small case study like this, but transactions that make sure that every change really is related to only the things it should relate to, right? I did remove the highlighting feature, but it would still highlight always the latest message that that you have personally added, not remote messages. Maybe let's add it again and see what happens, right? So we had here this we here had this style string, and we said that in the case that chatline.value.contains chatline of author message, so this should be an if, right? If this is the case, then we have color red, and else we just have an empty string. And now say style equals style string. Right? See if this compiles. It did. Where did Chrome vanish to? No one knows. And close it. Interesting. Let's open it. We do. Open both again. New messages are colored, but if we now connect them, only mine are colored, and from the others they are no longer colored, because these are really now different transactions, which in the semantics may or may not be what you would expect, but as you may have noticed, I could predict what would happen even though I didn't prepare this part, because once you understood the transactional model of Rescaler, it's clear that because this input is a transaction, it can only change the input when it happens, and when you get a remote message, it doesn't overlap here. Okay, so that concludes the chat case study. I hope you have learned something about how to write a distributed chat application. And interesting point of order, there's an interesting thing that's called state machine replication, which is a theoretical result that if you kind of formulate it very lax, it says if you can do a chat, you can do arbitrary distributed computations, because once you can have these ordered operations that you replicate, you can see them as inputs to like a state machine which can do arbitrary computations. So this shows kind of that this kind of strategy of distribution is like the distributed equivalent of Turing complete, which I mean is not super interesting maybe, but is a cute kind of result, and is also why a chat application is interesting for distributed systems. With that, I thank you for staying with me for so long, and good luck and have fun.